Hey guys, Ms. Gosling here. In this video, you're going to learn about critical density. By the end of the video, you'll be able to use Newtonian gravitation to derive the critical density of the universe. So let's get started. So our understandings, applications, and skills for this topic from IB are critical density and deriving critical density from Newtonian gravitation. This is important because it helps us understand the future of our universe. So we have a few different things that could potentially happen. So first, our universe could expand forever. Or maybe our universe is so dense that the gravitational attraction between matter and dark matter will eventually stop our expansion, potentially causing our universe to collapse back in on itself. So this third bullet point is kind of our fundamental question. Will a universe collapse back in on itself or expand together? Understanding the critical density of the universe helps us answer this question. So, critical density is the barrier between a closed and an open universe. When I say a closed universe, what I mean is a universe that is fundamentally four-dimensionally spherical in shape, so it will expand until it reaches a limit, at which point it will collapse back in on itself. An open universe, on the other hand, is a universe that is shaped kind of like this, like a saddle almost. It's going to keep expanding outwards, and it will expand and expand and expand, cool and cool and cool, and never collapse back in on itself. Now, there is a third so backing up, if our universe will be closed if the density of the universe is greater than the critical density. Because what that means is that we have enough matter in the universe that the forces of gravitational attraction will eventually cause our universe to collapse back in on itself. If our density is less than our critical density, then our universe is going to continue expanding forever. We have one special case where the universe's density is directly equal to the critical density. In that case, we call the universe flat, and we can understand it as essentially three-dimensional without any curvature, and it's going to just keep expanding forever, just like an open universe would. So we've talked a lot about why critical density is important for understanding the future of the universe. What we haven't talked about is what the critical density of our universe is and where it comes from. So we can understand, if we model our universe as just a big sphere of gas, we can understand its energy as being equal to the gravitational potential energy between the different gas molecules and the kinetic energy of those individual gas molecules. And for reasons you'll see in a moment, I'm going to go ahead and just flip the order of those two terms. So at critical density, the total energy in our universe is 0. So our kinetic energy will be equal to our potential energy. For our universe, kinetic energy is going to equal 1/2 mv squared. And our potential energy will be negative g times the mass of the universe divided by, times the mass of the universe times the mass of this kind of this little particle at the edge of the universe divided by its distance from the center of the universe squared. Or not squared, excuse me. So what this means is that 1/2 times the mass of a gas particle in our universe times its speed squared must be equal to the gravitational constant times the total mass of the universe times the mass of that gas particle divided by the distance from that gas particle to the center of the universe. So as we can initially see, the mass of that gas particle is irrelevant because the masses cancel out here. Now, let's talk about the mass of our universe. So we know, because we're interested in critical density, we haven't even talked about density yet. But we know that density is equal to mass over volume. So for our universe, our critical density is equal to the mass of the universe divided by the volume of the universe, which we can model as a sphere. So that volume is 4/3 times pi times r cubed. So now we're going to go ahead and plug that in for mass. So what that means is that mass is equal to 4/3 pi r cubed times the density of the universe. And in this case, since we're looking for the critical density, we're going to go ahead and write a little critical density in here. So that means that 1/2 mv squared, or 1/2 v squared is equal to g divided by r times m, which is 4/3 pi r cubed times the critical density. So let's go ahead and simplify. That gives us a critical density, or that gives us 1/2 v squared equals 4/3 times g times pi r squared times the critical density. Now, there's one more thing I can do to simplify. So what I'm going to do is I'm going to go ahead and write this as v squared over r squared equals 8/3 times g times pi times critical density. The reason I'm doing this is because I can use Hubble's parameter now in place of v and r. So if we remember, Hubble's parameter is found using the equation v equals h naught times d. So what that means is that Hubble's parameter is equal to velocity over distance. And in this case, the distance that this imaginary gas particle is from the center of the universe is given by r. So what that means is instead of v squared, so that means that v squared over r squared is equal to v over r quantity squared, which is equal to Hubble's constant squared. So in my equation, I can now write h naught squared is equal to 8/3 times g times pi times the critical density of the universe. And solving for critical density, that gives me that critical density is equal to 3 times h naught squared over 8 times g times pi. And there you have it, guys. This is the critical density of our universe. Now, just so you all know, this equation is in your data booklet. You do not need to memorize it, but I think it's important that you understand how I got from step 1 to step last. You should be able to derive this equation yourself using net total energy of 0, using the relationship between density, mass, and volume, and using the relationship between Hubble's constant, velocity, and distance. So let's go ahead and do a quick example. Evidence from the Planck Space Observatory suggests that the density of matter in the universe is about 32% of the critical density of the universe. State what is meant by the critical density, A, and B, at critical density, there is 0 total energy. Show that the critical energy of density of the universe is RC, which is critical density, is equal to 3 h naught squared divided by 8 pi g. So what I'm going to ask you to do is close your notes. See if you can answer these two questions on your own. Pause the video and try it. Seriously, actually try it. I'm going to go through the mark scheme on the next slide, so that way you can see what the answers are. Okay, so you guys have tried this question. Go ahead, take a moment, look at the mark scheme, and grade it yourself. It's really important when you grade this that you do not be too nice to yourself. It's very important when you're doing these questions for you to grade like you were an IB grader. So don't give yourself points you didn't earn, because then you won't learn from that. Instead, take a moment and look first at A. Look at the different options the answers you could have given. So you could have said it was the density of a flat universe. This word Euclidean, you've probably heard it before. In this case, it's another synonym for flat. What it means, a little bit more precisely, is just that Euclidean geometry works. And since Euclidean geometry assumes a flat plane, we can use it in this case as, again, a synonym for flat. Another option you could have given is instead of flat, you could have said zero curvature. So that means, again, the same thing, right? If something has zero curvature, it's flat. The density resulting in universe expansion rate tending to zero. So that means so with a flat universe, if you remember, we will expand and expand and expand until eventually we stop expanding, but we don't crash in on ourselves either. So there's 3 different answers that you could have given for what is meant by critical density, but you'll notice that all of them start with density of or density resulting. So the focus is that you do need to make sure you're using the word density in your question. For that second problem, if you look at this, you can see that what you're being asked to do is the exact same derivation that we did on the slide 2 before this one. So you have seen me do this derivation, and you can, I think, hopefully see from this why I told you need to make sure you understand and can recreate that derivation. I'm not going to tell you there's a 100% chance you get asked this on the exam, but there's a pretty good chance you get asked to share this derivation to show that you can do this derivation on your own. So I would recommend practicing it, working through it, and maybe even writing it out like you would a geometry proof, with the step and the reason for the step in 2 separate columns. So with that gives us the critical density of our universe. So first takeaway, the accepted value of the critical density of the universe is this value here. This is what you get when you take all the constants that we had in our critical density equation and all of the exponents, and you just throw it all on a calculator. You do not need to have this number memorized, but you should know how to get to it using the equation and constants in your data booklet. Second, if the density of the universe is greater than the critical density, our universe is closed. If it is less than the critical density, then the universe is open. And if it is equal, then the universe is flat. It's also important to note that a closed universe will eventually undergo a big crush and collapse in on itself. A open universe, I'm going to go ahead and cross off flat here, will get larger and colder forever, and a flat universe will grow to a maximum, but will not crush back in on itself. So with that, you have had an introduction to critical density. Go ahead and try doing the derivation yourself a few times and solving a couple of other critical density problems. Best of luck and happy learning.